Hi, Matt Malkan here today with our lecture, which is on the topic Our Home, the Milky Way, the Milky Way galaxy. But we don't know that yet. So I want you to take a look at this beautiful all sky picture here that was taken during the southern winter from someplace in the southern hemisphere. One picture is really worth a lot of words, but I'm going to stick a lot of words in anyway because you can really see the Milky Way best if you are in the southern hemisphere when in the winter down there, our summer, it's passing straight overhead and you just cannot miss the spectacular structure overhead, and it clearly wraps all the way around the sky. And so that's been known. Of course, you can see this without a telescope. It's completely obvious if you're not living in a big city and you can see a dark sky. It's the most prominent feature there. You cannot miss it. And of course, nobody missed it thousands of years ago, and it is a fuzzy patch of light that was not understood what its nature was. So I don't know. I guess we owe the Romans the name of the Milky Way because it sort of looks like a bunch of spilled milk. And there's various mythological stories about it. Most of the things in the heavens, the constellation and so on, were connected to mythological stories. And so I think there's something about spilled milk here also as well. And by the way, you might notice another band of diffuse light that didn't get its own name and story. It's not quite as obvious. Anybody see that in this picture? There, of course. See my cursor? Duh, that's the Milky Way, blazingly bright, especially in the southern hemisphere where this most bright concentration of it, concentrated around the direction of the constellation of Sagittarius, just knocks your eyes out there. But there's also, what about this vertical band? Do you see that? Vertical band of light is particularly noticeable around sunset and sunrise. That one, anybody want to guess what that is? I'll give you a hint. There's two exceptionally bright, quote, stars in this deep exposure picture here, which are actually planets. And they seem to line up with this band of glowing light, which is not the Milky Way. What is that? That is the glowing light from scattered sunlight scattering off of dust particles in our own solar system, in the plane of the ecliptic. It's called the Ecliptic Light or zodiacal light because it runs along the constellations of the zodiac here. And that's just a local phenomenon. And of course, just to make it absolutely clear, what's happening in our solar system, which itself is a flattened disk or a flattened plane, is nothing to do at all with the flattened plane of the Milky Way. They're not even at the same angle. They're at a completely different, randomly different orientation. All right, so let's get back to the Milky Way here. I guess there was not really much science done with it. If we lived in the southern hemisphere and astronomy had really, the scientific revolution had gotten going down there, we might have figured things out sooner than we actually did. Because you see all of these beautiful, very dark bands where there's an absence of light there. It looks like there's a lot of light behind there, but these dark bands seem to have blocked out the light. In fact, I think the Incas even had some constellations for these very dark bands here, which is intriguing. But the view from the northern hemisphere, you only see part of the Milky Way plane. It still goes all the way around our sky, but you don't have a spectacular view of some of the best parts of it. But anyway, nobody really knew exactly what it was until the first time a telescope was used to look at it. So I think I have to mention this. It's such an important piece of history of our understanding our place in the universe, and it goes back to our old friend and hero, and sort of martyr for the scientific method in astronomy, Galileo. And as you know, of course, he was not the first person to invent the telescope, although he did make some very fine telescopes by hand, because you couldn't really buy them on Amazon back then. But he was, so far as we know, the first person to carefully, systematically look at the night sky with a telescope. What a novel idea. Everybody else was trying to peek into, bedroom windows or assess military, troop motions and things like that. But Galileo, as soon as he looked at the Milky Way, he was struck by the first obvious insight. This is not milk. It's not just a diffuse glow. What it actually is the diffuse glow from myriads, thousands, he estimated, but actually millions or billions of individual stars. This is actually just individual starlight of vast numbers of stars. And I had the privilege actually of flipping through his observing notebook at the National Archive in Florence. If you're interested in that, for me it was a very big moment getting in touch with Galileo across many centuries. You can go see that in this YouTube video if you want to skip the beginning where we do the planets and things like that, because that's not part of this Astronomy 4 course. You can skip up to about 9 minutes where we see his attempt to draw what he saw through the telescope of the Milky Way, and he basically ran out of paper. There's so many stars there you could see in the telescope here that he kind of gave up. But anyway, just with that one drawing, just with that one observation, I would say perhaps just in an hour of looking through his telescope, he changed forever what our perspective of our place in the universe is, because he realized not only are there many stars that you can see, I don't know, a few thousand that you can see without the naked eye, which he suspected, based on Copernicus's correct model of the solar system, were stars just like the sun. What he realized, that's just the tip of the iceberg. These stars up here are relatively near us, close to the sun, but we are actually living in a vastly larger system. He didn't know the numbers, but we now know it's billions of stars, not just thousands of them. It is a mind-boggling one-step increase in our scope, the appreciation of how much larger the universe is. We're going from just a solar system with 8 planets and some other assorted rubble left over and one sun in the middle of it, to maybe a few thousand visible stars nearby us, a few hundred light years away, to billions of stars in a collection which seems to be organized pretty systematically in a disk or a plane, which we'll call the Milky Way. And so after Galileo's observations, it was never really accurate enough to just say, oh, that's the Milky Way up there. This is the Milky Way galaxy. It's a galaxy of stars. And for hundreds of years, that was the galaxy, and that was the only galaxy that we could be sure of. It's just about the only galaxy that you can see with the naked eye. And so the galaxy for hundreds of years kind of meant the universe. It meant everything that we know about. But still an enormous change in perspective. You could argue that that was really more important, more lasting discovery that Galileo made than practically any of his other discoveries he made with his telescope, of course, about the phases of Venus, the moons of Jupiter. Those are great firsts also, but this really tops them all for me in terms of ultimate long-term impact. I don't want to call your attention. All right, those are just like some airplane trails or something like that. Ignore that. What about these 2 little fuzzy patches that are so far south you cannot see them at all unless you're in the southern hemisphere? Those are not stars. They're fuzzy patches. If you look really carefully in the northern hemisphere, you can see another fuzzy patch that looks a little bit like it in the constellation of Andromeda. And these fuzzy patches, though, are brighter than Andromeda. And what the heck is that? Those are other nearby neighboring companion galaxies. And again, they look fuzzy simply because we don't have the magnification to see all of the stars that are in there. For historical reasons, these are named the Large and Small Magellanic Clouds. But anyway, of course, Galileo didn't know about that, and he didn't have a powerful enough telescope to realize these are also fuzzy balls of maybe a billion stars, certainly many millions of stars, hundreds of millions of stars in there. So that had to wait for much more powerful telescopes to come along. In fact, that really had to wait for the big telescopes in California in the 20th century to have that breakthrough. We'll get there in a minute, but I just wanted to see, there's already an interesting question just on this one picture. Such an interesting picture. So many things to notice there. All right, so why wasn't a lot of, aside from the absence of big telescopes to show that these galaxies are made up of stars, why wasn't our place in the Milky Way more evident earlier on? And as I said, part of the problem is just an accident that most of the astronomers during the scientific revolution were stuck in the northern hemisphere and didn't really have such a nice view, although it's still a pretty good view of the Milky Way. But there's another problem, which is, of course, like most people until the recent 20th century, 21st century, they were limited to just visible light that you can see with your eye. And visible light actually has a rather difficult time, as you noticed in the previous slide, traveling through the plane of the Milky Way galaxy. A lot of it is subject to absorption. Actually, you could see that in the previous picture here, all of these dark bands. In fact, it looks like in the plane here, it looks like we must be missing much, if not most, of the true light of the Milky Way if you can try to extrapolate what would be behind those absorbing clouds. And in fact, that is correct. We're missing a great deal of it. This is a close-up view where you can actually see this is along the plane of the Milky Way, but close in. First of all, you can see that there are just zillions, okay, well, millions and billions of individual stars. There's so many stars in this picture that they're just all gushed together. We don't have enough magnification. I've taken photographs of this region with large plates, this large, and it just looks like it's completely covered with pepper. I mean, there's almost no space between them on these plates. Of course, there's lots of space between the stars. That's because we don't have enough magnification. But especially the blue light doesn't get through. You can see sort of some of the yellow and red and orange light comes through. So what's the problem here? The problem is that short wavelengths, such as blue light in particular, are very susceptible. Think about a photon. It's a wave with a short wave. It's very susceptible to absorption if it encounters an obstacle, which might be a physical object, which is comparable in size to the wavelength of light. So we've already seen this before in the course. Well, what would be something that would be an obstacle to be comparable to the wavelength of blue light? A small particle of dust, an interstellar dust grain. They are very small and maybe less than a millionth of a meter, maybe a 10 millionth of a meter, but that's about the wavelength of blue light. So, and this was not obvious to people at all, that a lot of the plane of the Milky Way galaxy contains interstellar dust. This is interstellar matter that's not the stars. It may not even be producing that much light unless it gets lit up and heated. But there is a large amount of interstellar gas, and then a fraction of that, maybe 1% of that, has clumped together and condensed in the form of interstellar dust grains. And these are really opaque to short wavelengths of light. So if you really want to get a good view of what our galaxy, the Milky Way galaxy, actually looks like, from our perspective on the sun, you need to look at long wavelengths, and that was only possible fairly recently, where the interstellar dust grains are so small that the wavelengths are longer wavelengths can just bend straight around them, the same way that radio waves are not really stopped by small buildings and things like that. They're such a long wavelength they can go around them or through them. And the same thing happens when you look at the Milky Way, for example, with an infrared telescope or a radio telescope. Those are much longer wavelengths. Now you see really a much more realistic view. That's our Milky Way galaxy with an infrared telescope. And there's still some absorption here in the center. There's very clearly a strong concentration of light, not where we are, but over in the direction of the constellation of Sagittarius. But this actually is the full sky picture here. So the Milky Way is actually a band that wraps all the way around 360 degrees around the sky. You can verify this from the northern hemisphere and the southern hemisphere. So we're in it. We're not on the edge of it. If we were on just the edge, but we're not in the center either. The center is in this direction here. If we were on the edge of it, then it would stop at there would be some edge that you would see looking far enough out to a large enough angle. But the fact that we see it all around means that we're we're somewhere within it, inside it. Oh, by the way, there's a large and small Magellanic clouds visible in this infrared picture also. All right, so that was a good step forward, although this was only possible really when these new technologies were developed. Radio astronomers started studying the galaxy after that was developed during the war, as we discussed World War II. And infrared detectors were only available even much more recently than that. They were largely developed for night vision for military purposes. It all comes back, to technology partly being driven by us trying to defend ourselves. And so but there were other hints already about what the nature of our Milky Way galaxy was. Obviously, it's a disk, that's pretty clear, but what's our position in it? What's our location? That's a tricky question that people were actually thinking about carefully in the 1930s. Can I just take a break and just show you a few pretty pictures just for the heck of it? Here are some close-up views of interstellar dust. And you can see, if you have a large concentration of this, how completely absorbing it is of all light. Here's an optical picture. There's some interstellar gas in the background. Right in front here is this little hook thing, which if I zoom in on it, seems to absorb all the light in the back of it. Yep, there's a few stars in front of it here. You can almost see the three-dimensional structure. It looks like a big plume of dust, doesn't it? That's exactly what it is. That interstellar dust nebulosity is known as the horsehead, because this is one of the few nebulae where the name actually really does look to me like what the name is. I mean, that looks like a sort of astronomical horse head going around there. And so if you have enough of this dust, of course, it can be completely impenetrable by visible light. If you look through this in the infrared or radio, though, you can see right through it. So let's see if I've got any more pretty pictures of this. Oh, that's a beautiful one also. I don't know if this has a name. Maybe we could call that the Pony Nebula or something like that. This is a close-up view, so you can see more structure because the Hubble Space Telescope took that one. And so it's remarkable how opaque interstellar dust can be. But it makes really pretty pictures. So that just illustrates that. All right, and then this is sort of the money shot here. The upper shot is a visible photograph. Again, it looks like the one that we opened up with on the first slide here, of the Milky Way at night, and you can see a great deal of light's absorbed. You can sort of get a rough idea of where the plane of the Milky Way is, and you can get a rough idea of where the central concentration of the Milky Way might be. Here's a modern infrared picture, and you can see very clearly where the center of the galaxy is. And what I think is really remarkable is you can see just how flat the disk of the Milky Way is. This is a very flat plane of what? Of stars mixed in with interstellar dust and gas, the interstellar matter. And it's flatter than a pancake, really. In the old days, I used to say this is about the dimensions or the flatness of a DVD. Apparently, people don't really know what a DVD is anymore. It's very flat. All right, that's an interesting clue, and we're pretty close to the plane. We're pretty much in the plane vertically, but we're by no means at the center. So let's see if we can figure that one out. All right, this is a schematic. It's not a great diagram, but it does show how this was worked out. The key was to find something else that's associated with the galaxy, something else that's clustered around the center of the galaxy. It's in the here we are. This is the direction that the Sagittarius constellation is in. That was where the extra amount of starlight, the strongest, brightest amount of starlight in the Milky Way was present. Turns out that there are objects which are not at all in the plane of the Milky Way. In fact, they're in a more spherical halo. This is not really drawn very well here. But so if you look out of the plane of the Milky Way, you can see very far, relatively unobstructed. In fact, you can see out of the galaxy. Thank God for that. Otherwise, astronomy wouldn't have made too much progress. But anyway, you can see objects which are above and below the center of the galaxy and their globular star clusters. We already saw the globular star clusters before when we studied the evolution of stars, and they were very useful for that purpose. Now they're useful for another purpose, which is the globular clusters are giving us a three-dimensional view of our galaxy, and they show us how far we are from the center. Remember, we know the distance of globular clusters because we know the distances of stars in the globular clusters, and it's approximate. I'm going to say we're about 25,000 light years from the center of the Milky Way galaxy in the direction of the constellation of Sagittarius. Sagittarius, of course, is just a few nearby stars that makes a random pattern. Don't get me started about constellations. They're not even real physical associations of stars. It's just convenient landmarks that navigators used, and they attach mythological names to them and stuff like that. But everybody says that, Sagittarius is the direction where the center of the Milky Way is, so I'll use that terminology also. So a very large system. Of course, it's much larger than just the distance of us to the center. That's about 25,000 light years because we're not at the edge. You can see more Milky Way out here, in the opposite direction. It'd be towards the direction of Orion, which is the opposite direction from Sagittarius. Like the anti-center extends out. The entire extent of this disk of the Milky Way galaxy in which we live, probably about 100,000 light years. It just sort of tails off. There's less and less density, fewer and fewer stars, but you can detect some material from the Milky Way out to great distances. So we're in a completely random, typical, not special location in the plane in the Milky Way. It's very thin. You see, it's less than 1,000 light years thick, 100,000 light years from one side to the other. All right, so that was a good summary of what our knowledge was of the Milky Way. I'm going to say in about the 1920s or 30s. That was correct as far as it went. But then there was, of course, this interesting question, well, what about some of the other fuzzy objects in the sky that you can study more carefully with a telescope? Some of them show spiral patterns, the so-called spiral nebulae. These are clearly not stars. There's diffuse light in there. They might be made up of stars if only we had a big enough telescope that could tell us. And this is the interesting thing. As telescopes were developed, particularly the big ones, particularly out here in Southern California, more and more, and in Arizona, more and more of these spiral nebulae were being discovered in all directions of the sky. They're not connected to the Milky Way because they're not really concentrated down here in a plane. By the way, this plane of the Milky Way, if you remember from my previous lecture, is also where you find, for example, all of the pulsars that are known, the neutron stars that are producing pulsating radio waves. They're all in this plane, pretty much. So these spiral nebulae, then it became a great question. How do they fit in to the Milky Way galaxy? So you, of course, have grown up knowing that those spiral nebulae are actually their own little Milky Way galaxies. Our Milky Way here is just one, as you now know, one of billions of island universes or spiral galaxies that are spread over an even much larger region, much vaster region than just 100,000 light years, which still sounds like a pretty big region. That would certainly sound like a pretty big region to Galileo, wouldn't it? But that's nothing compared to how far the typical spiral nebulae are from us. But it's not obvious that that's what they were. At least it was not obvious to everybody, including some of the smartest and most reputable, distinguished astronomers, let's say in around 1920. There was a debate, the so-called island universe debate. So, this is the picture that would have settled it, could have settled it. I mean, how would you tell? If only we could travel outside of the plane of the Milky Way and get some perspective. If we could send a camera or a rocket or something up here, oh, I'm sorry, that would be really hard. We have to get up like 30,000 light years above and look back down on where we are. Then we would see a picture that would look something like this. Of course, it would take hundreds of thousands of years to get there. Then it would take 30,000 light years just to send the message back. Can't send the photograph back at faster than the speed of light. But anyway, if you could get out of the Milky Way and look down, it probably looks a lot like this. In fact, there's direct evidence now from radio astronomers that there are indeed spiral arms. See these spirals here? Concentrations of extra gas and interstellar dust and young stars in a spiral pattern here. But so it should have been, I don't know, it was not completely obvious. Some other people had a different interpretation of this. Given the data they had at the time, it was not a crazy interpretation. Their interpretation, they had pictures of spiral nebulae like this, but the pictures weren't very good. And so they said, hey, maybe there's a different idea. Maybe these are nearby. Maybe they're in our neighborhood of the Milky Way. They're local objects. They're not even outside of our Milky Way galaxy. These might be clouds of gas around individual stars. Not such a crazy idea, is it, actually? Maybe this is going to form a star in the future. Maybe it's in the process of being born, and it's accumulating gas down here in the middle, and this interstellar matter has collapsed down into a flat disk, which is actually, could it be a protoplanetary disk? What an interesting idea. We live in a flattened system of planets today. Maybe there was a disk of material around the sun when it was formed several billion years ago. Very strong evidence that that's true because we can now see that happening around other young stars. So that's an interesting idea that is a completely different view of the spiral nebulae. What was the way to settle the debate? There was a fake way to settle it, which really messed up everything. I just have to tell you this just so you can get a little feeling for how tough it is to be, an astronomer relying, as all scientists do, on observations of the universe that may be imperfect. You could see, if you took multiple pictures of one of these systems, you could see how long it takes to spin around once. If you could take pictures maybe spaced over 10 or 20 or 50 years, see if this thing is turning. That was actually done by some people who were thought to be very careful at measuring very small shifts in the positions and motions. It's hard to even find out what blobs you would use here to see if it's turning or not. That's a tricky bit, actually. These blobs turns out, are clusters of stars. So it was not very easy to make these measurements. They were very difficult. In fact, they were too difficult. In fact, the claimed results, I won't tell you the guy's name who became famous for measuring this. I think he claimed that the Great Spiral Nebula in Andromeda, I think he claimed that it was going around once in, 5 or 10,000 years. Well, that immediately proved that it was not at a vast distance outside of the Milky Way. If these measurements were right, it certainly can't be turning around faster than the speed of light. It would have to be a small object. It would have to be only maybe a light year across or something like that, a local object, except those observations turned out to be incorrect. The motions are much, much slower than that, and it actually takes these spiral arms tens to hundreds of millions of years to turn around once. They're vast systems. Even though they're spinning around pretty fast, they certainly aren't going at the speed of light. So that was a bit of a red herring there. What was the actual proof here? If this really is an island universe of its own collection of 100 billion stars, just like our Milky Way is, goes back really to Galileo's telescope, then a bigger telescope would show what? This diffuse light, a lot of it, especially in the middle here, is what? It's being produced by the light of millions or maybe billions of individual stars. So if we had a high enough magnification telescope with enough sensitivity, we would take photographs here, and this diffuse light would resolve out into vast numbers of individual stars in the other galaxy. But of course, they're so far away, they're going to be much, much fainter than any stars that anybody's ever been able to see before. Really, that was one of the motivators for building the biggest telescopes, and the problem was on the table. Everybody was thinking about this problem. I would say, for example, at Mount Wilson Observatory in the 30s, and it's an interesting story. I got to tell you the story. Allow me to digress for 1 minute here. Walter Botta was a great astronomer working at Mount Wilson Observatory with the beautiful world's largest telescope at the time, the 100-inch telescope. It's still there. It still works. It's a magnificent telescope. And he kept taking deeper and deeper, longer exposure all night long. Sometimes they would do 2 or 3 night exposures where you take the photographic plate, put it away during the day in the dark, put it back in the telescope and continue exposing for 3 nights long to try to see if he could get enough sensitivity to resolve the Andromeda Nebula into stars. I think that what really eventually put him over the top was kind of an interesting coincidence. The outbreak of World War II, Germany was declared our enemy to the death. And 2 interesting things happened at this time. We also managed to get into a war with Germany's ally, Japan, and there was concern, maybe it was overblown, that after what they did to Pearl Harbor in Hawaii, they might come and attack Los Angeles. Really not practical. But anyway, Los Angeles was under a blackout for years during World War II. This was the darkest the skies had ever been for, since the history of the 100-inch telescope had been around. Very good for doing deep, long photography when the light of Los Angeles, which was pretty brutal in 1940 or 1941, was turned off. Then there's another funny bit, and I really still think this is interesting. Walter Botta was a German national, and so he was considered to be under suspicion that he might be loyal to the Nazi regime in Germany, although he detested it. How do you prove that? He I believe had naturalized to become. He was in the process, or he had become an American citizen. Now, you're just not going to believe this. He's an astronomer. He wanted to spend all of his time at Mount Wilson. He was not able to locate the papers, his naturalization papers, proving, no, I'm a loyal American here. And although I think he was, what was the punishment of this? I love it. The punishment, since he really couldn't prove it, he was a bit under suspicion, is, Walter Botta, you're under house arrest for the entire war. You have to stay at Mount Wilson for the duration of World War II. Exactly what he wanted to do, wasn't it? So he spent many, many nights on the Mount Wilson 100-inch telescope, and he did resolve the stars. That proved that all of these vast numbers, there were millions of these spiral nebulae discovered. Now we know there are billions of them, are themselves little Milky Ways. So not only are we just one star off to in some outskirts of the neighborhood of the Milky Way galaxy, which itself is 100 billion stars, but our galaxy, the Milky Way, is just one of hundreds of billions of comparably large and well-populated galaxies. So that is hundreds of billions of stars like the sun. It's a mind-boggling number. I mean, humans' comprehension has a difficult time with such large numbers. Now, let me get back to one other point, and an excuse to show one more beautiful picture here. I was kind of complaining about interstellar dust a number of slides ago. Oh, it doesn't let us see the whole Milky Way. It got in the way. It was a bit of a nuisance. We finally solved the problem. It's not just that the interstellar gas, it does something good also. It is relatively dense, cool material. I said there, it's dense, it's cool, it's relatively low temperature, some of this stuff is. And this is a surprise. It can be so dense that it actually has its own gravity, which can actually pull it together. In fact, that's really the only way we know of that new stars could be born. And in fact, it's the interstellar matter, the space between the stars, which, by the way, as we saw earlier, has been recycled, maybe numerous times by previous generations of stars that died and exploded and sent out blast waves of gas into the interstellar matter to replenish it and recycle it. That same interstellar matter can form stars in the plane of the Milky Way galaxy today. It is happening today. And so this is a site where it's happening. There's a number of stars which are forming out of this. This is a very large, dense cloud of gas, and a number of stars have born out of this because it collapsed down until it got to very high density. Finally, some of the densest cores here got up to millions of degrees. In other words, they switched on nuclear fusion reactions. They became stars. So that's really why the interstellar gas is of so much importance, because you still see stars forming at a rate of about one star per year somewhere in the disk of the Milky Way galaxy. It's a very big disk, so that might not be such a high rate. It was higher in the past when there was more gas supply around, when not that much of it had been used up making the first generations of stars. All right, so very quick, since this is really not the purpose of Astronomy 4, very quick summary of how stars actually are born in the disk of a galaxy like the Milky Way. You have the densest clouds of gas at fairly low temperatures. That means low pressure. We need low pressure. And you got to remember, and this applies, we're going to see this applies throughout the universe. This is basically the reason we're here. Over and over again, gravity is an inherently unstable force, unlike other forces we're familiar with. Why is it unstable? Why? Because think about what happens when you have a slightly overdense region that has a little bit more gravity pulling itself together than the rest of the other locations in the disk of the Milky Way. That slightly overdense region wants to pull the material together and make it denser. That's what gravity wants to do. What happens if gravity succeeds in pulling it a little bit closer together to make it a little bit denser as it wants to? What's the result? The result is now that all of the forces between all of these particles of mass have increased. The gravity's gotten stronger. It got amplified because it managed to pull things closer together. It's an inverse square law force. So if you make that denominator, which is the distance or the separation squared, you make that smaller now, the gravity gets bigger. You see which way this goes? That's a positive feedback loop. That means that the source of the gravity tends to act in a way which will amplify the gravity. That's an instability, because then that means that the denser gas, feeling more gravity, will have a tendency to collapse more and condense down to smaller separations and get even closer, causing the gravity to get stronger. It's an instability. Once this starts going, it can lead to a runaway collapse. And that really is how stars form. They'll collapse all the way down until what's going to stop it? Until so much pressure, until the temperature builds up so much at the center of one of these collapsing cores that basically gas pressure will be strong enough to hold it up. When basically that pretty much happens at the time that nuclear fusion reactions switch on. That's the end of this collapse. Right? Then, as we've seen in our discussion of stellar evolution, then you have a star coming down onto the main sequence, and it's not going to collapse anymore until maybe later at the end of its lifetime. So that's my whole summary for how stars are born, and you just need this dense interstellar gas. That's a nice picture in the background. It's a dense interstellar gas where stars have been forming over the last thousands of years. So that's really pretty much all my insights to that. It's not really essential for understanding most of the rest of this course, but it's nice to know because that's how the sun got here. And there was some leftover material that couldn't collapse all the way in. It orbited around a disk. It formed planets, Earth being my favorite one of them. Now, this is possibly useful to know. Not all of the gas, presumably the Milky Way started out as a large disk of mostly gas, right? There were no stars initially, maybe it was all gas. But it does not all turn, it doesn't all collapse, the way I said, into stars all at once, which is actually a good thing. That's fortunate it happens. Because what happens is, here's an interstellar gas cloud that did start collapsing. The central, densest parts of it formed these new stars. These are very young stars. They haven't been on the main sequence very long. How do I know that? because it includes some very high mass stars that might be 10 times the mass of the sun. They only have a short time, maybe tens of millions of years, to be on the main sequence, and yet I see them here on the main sequence. Right? These are young star clusters. Remember, we used that. We looked at where the main sequence is. This main sequence turnoff, there is no main sequence turnoff. This is very high mass stars in it. And as soon as they form, they put out a lot of energy, and they begin to disrupt the cloud of gas that formed them. So that shuts things down. So that means this gas will have to wait. It might have to wait hundreds of millions or billion years until new stars are formed. That's why stars are still being formed today. We still have interstellar gas that's recycling, except now the fun part is there have been generations of stars dying, enriching this gas in heavy elements. In fact, you can see the green glow here, which is oxygen. You may remember that. So the new generations of stars that are forming today in the Milky Way have substantial contamination, several percent, heavy elements, and that leftover heavy elements is what's going to make planets around those stars. So we know it's likely to happen. It is not a freak accident. It is a natural byproduct when stars form today. They're going to have planets. They're going to have planets made of heavy elements, terrestrial planets, rocky planets like the Earth, which they're hard to find, but we're now finding them. So again, that's not the main purpose of this course, but I thought you would like to know how closely connected we are to all this action that's going on in the Milky Way's interstellar medium, the interstellar matter between the stars. Later on, these are still relatively young star clusters. Actually, this is the Pleiades. You can see just the brightest 6 or 7, depending on how good your eyesight is. When Galilei looked in his telescope, he realized, my God, there's dozens, there's hundreds of stars here. They're born together in a cluster. Most of the gas out of which they formed, although this is a fairly young cluster, has now been blown away. And so you just have the star cluster left there. All these little faint dots are stars behind in the background of the Milky Way. All right, so I think that's really pretty much all I wanted to say. What we're going to find out, and this is going to be interesting when we look at very distant galaxies, we're looking back in time, we'll see that later in the course, presumably applies to the Milky Way also. And I said this before. Although the Milky Way currently still manages to crank out, on average, 1 or 2 stars a year, it's pretty good, although it is a huge galaxy. It was doing much better billions of years ago. When the Milky Way was young, it was probably exceeding this by factors of 30 or 40. Maybe the Milky Way was putting out 50 new stars, many of them like the sun, every year. Wasn't that impressive? I know you're getting a little tired of old guys saying this. Everything was better in the old days. How many times have you heard people say that? Well, it's true of the Milky Way. Even the Milky Way was better. Yes, it's still forming stars now, but it was doing it so much better in the old days. Of course, the old days are billions of years ago. I wasn't there, even though you might think I'm that old. But one of the things that's interesting about this is that most of the stars that are formed in the Milky Way, of course, are going to be stars like the sun. That is a very typical star, or less massive than the sun. Rarely, occasionally though, a very massive star is going to be born. Those are, as we've seen, the rare ones, but those are, to us, some of the most interesting stars because they're the ones that are going to have enough gravity to have advanced nuclear fusion reactions and then go supernova and produce the vital heavy elements on which life depends. So I thought I would mention that there. When these massive stars form on the upper main sequence there, they are very hot. They are emitting a lot of ultraviolet photons. This makes them very, very noticeable. It's a little bit like, remember a planetary nebula, which wasn't really a planet and so on? That was a very hot white dwarf star. The ultraviolet photons from the surface of the white dwarf before it cooled off were making the planetary nebula shine with emission lines. This gas was glowing. We looked at that. By the way, some people didn't know the reason why a planetary nebula ends. It's not because the white dwarf cools down. That takes billions of years. The planetary nebula expands and evaporates and just diffuses into interstellar space. And that's what's happening in this nebula too. So the most beautiful nebulae, this is Malkan's rule of art shots in astronomy. The most beautiful art shots in astronomy are either dying stars or stars being born. So here's an example of stars being born, and they're producing, there's a lot of these hot stars here producing ultraviolet radiation. It's absorbed by the hydrogen gas, giving a very characteristic pink glow. That's from the level 3 to the level 2 transitions that an electron makes in a hydrogen atom gives you this pink emission line. I can tell you what the wavelength is, 656 nanometers. And it's beautiful. And there are some galaxies where this is going on today spectacularly, and where many stars are being born, and you can see the hot stars causing this hydrogen to glow pink across an entire galaxy. Isn't that a beautiful view? I'm going to end with this one right here. You see this beautiful spiral patterns. All this pink glow is actually glowing hydrogen gas that's being lit up today by very hot stars that have formed recently. Looks like the hot stars are really forming in a spiral wave pattern here. That is very common. It's also true in the Milky Way. We don't live in one of those spiral arms now. If you were looking down in the Milky Way, we've drifted out of it now. We're not a young star. We're an old middle-aged star, 5 billion years old. But galaxies, when they were young in the past, were all lit up with all of these young stars. All of the gas was glowing, which makes them rather distinctively easy to find. And that's how we use them. So in the final lectures where we trace back the history of the universe, we're going to be able to see a galaxy like this at incredible distances. It would have been unimaginable to Galilei. It would have been unimaginable to Walter Botta and even probably Hubble. The people that were working at Mount Wilson would just be amazed if they knew how far back we can see the youngest galaxies today. And of course, that's the purpose of the James Webb Space Telescope, which we hopefully will be launched successfully and deployed without breaking next year. So we'll talk about that in the next lecture.